our second presenter, which is Sophie Roman. She's an associate professor at the University of Orleans, and she's gonna talk about she's used microfluid experiments to investigate subsurface processes.
Thanks. Thank you for the introduction and thanks for the invitation. So I will also talk about microfluidics and for geosciences, and I will give some examples of what we can do with this kind of experiments. So, okay. So a little bit of background and of context. So the kind of processes that you are looking at are hydrogeochemical processes in porous media. So for example, when for the process of CO2 sequestration in geological formation, if you look at, so you inject CO2 in a deep saline aquifer, and if you zoom in and you look at the pore scale, you will see that your CO2 will displace the fluid that was initially there. Usually it's brine, and so you have a multi-phase flow problem, and part of the CO2 will get dissolved in water, so that can lead to some reaction to alteration of the wettability. So you have all these kind of processes. So for so for this kind of process, some of the main questions that we have is to be able to evaluate the storage capacity of a reservoir, to optimize the injection process, and also to ensure a safe and a long-term storage. You want your CO2 to stay there and not to go back to the atmosphere. Another process is when you have groundwater contamination. So for example, if you have a contaminant that forms an immiscible phase with water that gets trapped in your porous media, it's very difficult to remove this contaminant. One way to do remediation is to use nanoparticles that will help to remobilize the contaminants, or that will react with the contaminant to neutralize it in a way. So in this case, we want to be able to first to predict where the contaminant will be distributed in the porous media, and how we can actually target a contaminant with nanoparticles, how we bring these particles to the contaminant for remediation. So our approach is a multi-scale approach. So we need to at the end, we want to understand the processes at the field scale, but for that we need different scales of understanding, and I'm mostly focusing on the pore scale, and it's not super convenient. Okay. Okay, and so for that, in our lab, we combine numerical modeling, experimental modeling, and also some characterization to try to get a deeper understanding of what is happening at the pore scale before upscaling to larger scales. Okay, and with this approach, we are trying, for example, to capture the space and time evolution of interfaces. When, for example, you have an interface between oil and water, or between air and water, to predict the amount of fluid that will get trapped in the porous media, and to see the role of pore scale events on the overall fluid front behavior, and also for reactive transport to understand the consequences of mineral reaction on the properties of your flow and of your porous media. So my approach is microfluidics. So you already know a little bit about that. Yeah, just the idea is that we etch a pattern on the substrate, and the substrate in our case can be made of silicon, glass, or PDMS. It's a polymer, depending on the process that we want to study, on the resolution that we need, on the fluids that we use. And it's covered by a transparent plate for visualization. And the pattern that we etch in this substrate can be of various complexity, again depending on the process that we want to target. So we can use very simple channel with successive pores, dead-end pores to trap a fluid, for example. Or we can use more complex geometries that are drawn from images of real rocks. So here it's sandstone and here it's a carbonate. And we can even incorporate reactive grains to the porous media. Okay, so this is my typical setup. So the micromodel, we place it under a microscope for visualization that is linked with a camera. And we have different way of injecting fluids in our system, either by controlling the flow rate or by controlling the pressure, again, depending on what we want to study. And with all of that, we obtain sequences of image of our process that we analyze and that give us information and that we can actually quantify the processes. That's annoying. Okay. Anyway. Okay. In our lab, we are working also a lot on improving the methods to be able to measure as much things as possible in our after our experiments. So, for example, we developed a method. We used a method called particle image velocimetry. And we apply it for complex porous media geometry, where the idea is to put particles in our fluids as tracers. So here you can see in a micromodel particles flowing, and we use them as tracer to measure the velocity field. One other experimental challenge is to measure the chemical evolution of the system. So this is what Jenna has already presented, and what we did together to use micro-Raman spectroscopy to get an idea of the chemical evolution of a system in real time during microfluidics experiments. We are also working on studying electrical signatures. So for those of you who are doing you are using geoelectrical methods. So we developed a microfluidic setup that includes electrodes to directly measure the electrical signatures of the processes. And here the idea is that we can at the same time measure the electrical signatures and see everything. So, and to have really an idea of how to relate what is going on in our microfluidic system to the electrical signature. And another and we also work on controlling the wettability of the micromodels, because wettability can be very important for some processes, as we have seen this morning. And we have one student, Victor, here, who has you can see his poster, who is working on injecting a plasma inside the micromodel to change the wettability. Okay, so I'll not say more about that. And so with this kind of setup, I will present two examples. One example of two-phase immiscible flow and one example of reactive transport. So I will talk about flow regime during drainage. So again, as you have seen this morning, when we have one fluid invading a porous media that was initially saturated with another fluid, you will have different flow regimes that depends on mainly on different dimensionless number. So mainly the viscosity ratio, so the ratio the viscosity between your fluids, the capillary number, which is the ratio of the viscosity over the surface tension, and also the bond number that takes into account the gravity. And so depending on these numbers, you can have a stable front when your fluids, your non-weighting fluid is displacing your weighting fluid, or you can have some instabilities. The idea is so you will have different front behaviors that will lead also to different residual trapping, and we still need to investigate that. Okay. And one way to study that is to use pore doublet models. So pore doublet models, it's very useful because it's a simplified model of a porous media. So as was presented this morning by Danny, so this is the kind of model where you have So these are just different representation of a pore model, or of a pore doublet. So where you have one inlet channel and then two parallel channels that then reconnect at the end. And the two channels, they can have the same diameter, or like here, they can increase in size with the distance from the inlet, or you can have sinusoidal channels. And what is interesting with this kind of models, as we have seen also this morning, is that you can develop.
Just click on the change on the other
Yes. Too much. Okay. Is that you can so you can have models that will describe how the position of each meniscus in each channel as a function of time. So here, for example, it's for this geometry when you have a stable invasion. So both channels can be invaded at the same rate. So here you have the two positions that are superimposed, or you can have an unstable invasion where one channel here, so the channel 2 is invaded, and the other, the interface does not, so will be invaded less rapidly. And we can, with this kind of model, we can also do experiments. So we try to always combine the models with the experiments. So this is one of the experiments in this kind of pore doublet model for an unstable invasion. So this is the work of Nathan, who is also here, and I'm also advertising for his poster if you want to know more about his work. But then I will mostly talk about pore doublet models when we have sinusoidal channels. So we did microfluidics experiments where we have two channels and with successive pore swath and pore bodies of the same sizes for both channels. And we wanted to have a look at the wall of pore invasion on the flow regimes that then we observe. So with this kind of micromodel, the idea is that we first saturated with a wetting fluid, and then we inject a non-wetting fluid, and we did that for different pairs of fluids, so for different viscosity ratio and for different flow rates that leads to different also capillary numbers. So we try to have a various range of parameters. And so what we observe with these experiments, so first, okay, so wait, it's not. So if we have quite high flow rates, both channels will be invaded at the same rate. You can see it's air entering the micromodel, and here, if you look at the position of each interface in each channel with time, they are both superimposed and they are both invaded at the same rate. And we also use the model of Moebius and Daniel to characterize this flow regime. Here also what we see when we have the pore invasion is that we have some fluids that is less behind, so some water that is less behind at the curvature of the pores. So we have some residual saturation in this case, and some water that can then play a role in, for example, in viscous dissipation at the interface between air and water. So now, if we are a much lower flow rate, so we are dominated by capillary forces, we have this regime where we see, so only one channel is invaded, and now we see these successive end jumps. So you see, so the interface is spin at the interface, and then it will invade the pore by this sudden jump. And you can see these jumps here when we look at the position of the interface with time, with this kind of steps made by the interface, and we can also capture that with the model. So, and what was interesting, yeah.
When you have some kinds of color inside the
inside the what? Sorry.
Like when it invades the pores, then
it's
it's turning, or there is something.
It's film. It's the interface that is more or less attached to the wall of the micromodels, and it creates some.
Film.
Yeah, some films. It's some films actually.
Water film.
Yeah, yeah.
What's the defending fluid again?
So it's water and air.
Okay.
Yeah. but we also did it.
Did you introduce heterogeneity by, did you want to introduce heterogeneity or just kind of manufacturing the differences?
Sorry?
The size of the channels.
So both channels are exactly the same size. And so the fact that one is invaded and not the other, so in the model we put a little heterogeneity to have always the same one that is invaded, and here in the experiments then it really depends on, maybe during the fabrication process you have one that is a little bit smaller, or yeah, and then this one will be invaded, but they are the same size.
Does it always go in the same channel if you?
No. So if you do the experiment with the one that you have fabricated, the same, yeah, with exactly the same, I guess, yes, it will be on the same side, but then no, it depends. Yeah, if you fabricate again, because it depends on the fabrication of the mold and on the fabrication of the PDMS, so, yeah.
So why there are 3 capillary numbers on this plot?
Here?
Yeah, this is log -3.9, so there are 3.
So here it's the viscosity ratio that is different. So it's you have also, so it's a range of capillary number because it's different experiments with different, for the capillary number so there is a flow rate that we put, but we measure it also at the inlet here, and this is how we define our capillary number based on this flow rate, so it's just different flow rates.
So it behaves the same way? So
yes, you have a range of capillary number and a range of viscosity ratio for which you will always have this capillary flow regime. And it's the same for the previous one, the stable regime. You have a range of capillary number and a range of viscosity ratio for which you will have the same regime. And you can actually put that on a diagram that I would just show.
From the previous one is that we just change the shape of
No, the difference is here it's the flow rate, mainly, yeah, or it can be the. So here it's a much lower flow rate, so much lower velocity. And you have a regime that is in between this stable regime and this capillary flow regime. That is a crossover flow regime. So in this case, the invasion is by end jumps, and both capillary are invaded, but not at the same rate. So it's really a regime that is, and it's for intermediate capillary numbers and intermediate viscosity ratio. So what is interesting is that in this case we displace, so after pore invasion we have displaced all the water that was initially present. So this is a regime for which we have less residual saturation. So from these experiments for various capillary numbers and viscosity ratio, we can have a stability diagram with our different regime. And here in this work, what was interesting that we were able to really link the pore invasion mechanisms to the different flow regime, both experimentally and with the pore doublet model. And that this kind of model can really capture the drainage dynamics. So now we are also investigating what is the walls of the wetting layers, because as you have seen, in some cases we have really wetting layers that are remaining at the corners of the pores. So Nathan is investigating that now. And so now I move to another topic, which is now on reactive transport, but also using microfluidics, how we can control the flow of colloidal particles using concentration gradients. So why we want to do that? So the idea is to use a phenomenon that is called diffusophoresis. So diffusophoresis, it's when you have a colloidal particle, like the particles that I show for the PIV, for example. So here in pink. And if this particle is under a concentration gradient, so for example, you have high salt concentration here and a low salt concentration here, this particle will move just due to the concentration gradient, either toward higher concentration or lower concentration. It depends on the property of the salt and on the properties of the particle. So this is called diffusophoresis. So this phenomenon is now well known. So it has been studied at the scale of a colloid or at the scale of simple channel geometry. But at the scale of a porous media, there is a very few study about that. So the idea is to say that if in a porous media we have a source of concentration gradient. That can be a mineral reaction, that can be a pollutant that is degrading. Will this source of concentration gradient will be enough to drive particles, and for example, for remediation, can we actually use that to drive particles for remediation? So, but also one of the questions is that in porous media we can have strong, it's not super strong, but we have advective flux in natural environments with usually velocities around micrometer to millimeter per second. And diffusophoresis velocities are mostly in the range of micrometer or less per second. So yeah, we don't know if actually diffusophoresis will have an effect in the kind of environment that we are looking at. So to study that, we wanted to see the impact of a source of concentration gradients on the transport of colloids. So our experiment is this one. So we have a channel, a straight channel made of PDMS, and in the middle of the channel we put a crystal of calcite. And the thickness of the calcite is the same as the thickness of the channel. So here you have a picture of the calcite. So the flow is going around the calcite and not on top and bottom. So we used a similar setup a couple of years ago to study actually mineral dissolution at the pore scale and to compare with numerical models that were developed. So now with this setup we have different solutions. So either we inject a solution that is saturated with calcite, so we have no reaction, or we inject solution with lower pH, and so we have dissolution of our crystal of calcite. And within this solution we put microspheres, so colloidal particles of 1 micron in diameter that have different properties, and they are either negatively charged or positively charged. And we studied two cases. One case where we imposed a flow rate of 2 microliters per minute, and one case with no flow. So first what I'm showing is the case where we have no colloids, so just the dissolution of the calcite with time. So we always use the same concentration of acid and always the same flow rate. And if we have no colloids, this is the dissolution of the calcite for 17 hours. And from this kind of experiment, we can measure dissolution rate by looking at the area of the calcite with time. So now, if we put particles, so first particles but with no reaction as a control experiment. So if we have our calcite and particles are suspended in the solution that is saturated with calcite, they will just flow around the calcite, and with micro PIV we can measure the velocity field, and we have a classic Stokes flow. And now if we have reaction, so it's exactly the same setup, but now we have the particles suspending in acid. So here it's particles coated with carboxyl group. And what we see is that with time, the particles will aggregate to the calcite. They will form this large aggregate. And so you can see here the formation of the aggregate. We can measure the size of the aggregate with time. So we see that particles are focusing towards this source of reaction of concentration gradients. And also in this case, as long as we are injecting the particles, they continue to get aggregated to the calcite. So the source of concentration gradient is preserved. They form kind of a coarse layer of particles that still, and we have still some chemical reaction. And in this case, the aggregation of the particles is reversible. So if we stop the reaction, most of the particles, so this is after reaction, most of the particles will get displaced again, and they are not aggregated anymore to the calcite. So in this case, yeah.
Could you explain what is the forces that keep them aggregated?
So I think in this case it's electrostatic forces. That, because then as soon as we remove the source of concentration, so it's diffusophoresis that makes them focus, but then it's probably just electrostatic forces that but as soon as we stop, they get displaced. And we have another case where if we use sulfate coated particles, it's the same. So with time, particles will aggregate to the calcite, but in this case, they form a much denser aggregate. And we think that there is some kind of precipitation. So they form a kind of a precipitate. And now this layer is permanent. And it will not, even if we stop the reaction, the aggregate will stay there. And in this case, we stop the reaction. So at some point, this is the size of the aggregate with time. It increases, but at some point, we can no more aggregate particles because we have stopped the reaction. So in this case, we have a permanent effect, and we can actually control the source of concentration gradient. We can stop the chemical reaction with this process. If we look at the velocity field around the calcite, here it's before reaction, and here it's during reaction. We cannot really measure this diffusophoresis effect because we have quite strong advective flux. So what we measure is actually the advective flux around the calcite. So then to evaluate the importance of diffusophoresis in our system, we did experiments but with no flow to see if it's actually diffusophoresis that we have. So now we do the same experiment. So we have our piece of calcite in the middle of the channel. We put it in contact with acid and with particle, but we have no flow. And so here we can see actually that particle will focus towards the calcite for about 1 hour. So here it's the velocity field that is plotted. So with velocities that are below 1 micron per second, so it's very, very slow velocity, but enough to actually aggregate particle towards the calcite. And after 60 minutes, it stops. So the particles, they will just move away.
So why does it stop?
Because we have no more, so the reaction will stop because we have no more acid that is there, that is in contact with the calcite. Yeah, it has been consumed. Yeah.
Sorry, Sophie. You mentioned before that if you use switch for fresh solution and you don't have any more reaction, the particle they don't read off, they attach and.
So it depends. So with the carboxyl particles, if we stop everything, they will leave.
Okay.
So yes, it was we observed. But with the other kind of particles, they will stay.
And do you know why?
So we think that with sulfate particles, there is probably a kind of a reaction with a product of the calcite dissolution that makes maybe some. Yeah.
And the particle is made up of what? The colloidal particles?
So they are all polystyrene, but they have different coatings.
And the one that gets stuck around the...
And the one that gets stuck, it's coating with sulfate.
Oh, good.
Yeah.
Do you have a way to measure the local concentration of acid in your sample?
Yeah, that's the next step. Yeah, we have one student working on that. Yeah, we would like to do that. So there is a different way of doing it. So we can also do it with simulation, with the dissolution of the calcite, but we would like also to do it experimentally to have an idea of the concentration gradient, at least around the calcite. So, okay.
Sorry?
Yeah.
So in the velocity measurement, so you have pure diffusion with reaction. But when you do PIV, you don't consider the diffusion, the velocity due to diffusion.
So when I do PIV, I just measure the velocity of the particles. So actually, when they are just diffusing, so it's the same. When they are diffusing, the particles, I will just see them a little bit moving around, but with no preferential direction and with very, very slow velocity. So I know that it's diffusion. And when and here it's really diffusophoresis that makes them move towards the calcite. But when I measure the velocity, I cannot separate the advection and diffusion. I just measure their velocity and then I see. So here it's the same measurement, but for the sulfate particles. So to explain that it's actually coming from diffusophoresis, when we have our piece of calcite, when it's dissolving, it will create some species in solution, and so we have a concentration gradients that go outward of the calcite. And because the different species that are produced, they have different diffusivity, This difference in diffusivity will make it will not have the same charges, plus and minus charges on the both sides, and you have a local electric field that is created. And this is why negatively charged particles are attracted by the calcite that is dissolving. Oops. So to predict diffusophoresis, so there have been some models. You can find some models in the literature. So the diffusophoretic velocity depends on diffusophoretic mobility and on the concentration gradient. And this diffusophoretic mobility depends on the properties of your salts and of your particles. So you can measure that or predict that. And so in our case, we consider that so the concentration gradient depends only on the distance from the center of our calcite, on the radius r here. And if we plot, so here first, let's look at the gray line. So the gray lines, it's the theoretical diffusophoretic velocity that we expect in our system. And I plotted it for two different zeta potential of the particles. So actually I choose the two extreme values that we will have in our system. Because in our system, the zeta potential of the particles will depend on the pH. So it will depend where the particle is here is in the system. So these are the two gray lines. It's the boundaries of diffusophoretic velocities that we expect in our system. And then, so the blue and the red, it's actually what we measure for carboxyl-coated particles and for sulfate-coated particles at the beginning of the static experiments. So we are actually in the range of diffusophoretic velocity, with velocities that decrease when we go away from the calcite. And then after some time, we have no. Actually, here it's negligible velocity, so we have diffusive behavior. So after some time, we lose that. So it's to show that it's actually diffusophoresis that drive our particle towards the calcite, and that in the case when we have no flow, it will last for about 50 minutes before, and then we have no more reaction and no more diffusophoretic effect.
Why is it log of concentration? Gradient of log of concentration?
It's in the different models that is used. This is how it has been derived.
It's a really weak effect.
Yeah.
That's why it's almost flat.
So here, then it just depends on the position of your. So this gradient of the log will give you in our case, if we consider that we have the gradients that just point outward the calcite, it will just depend on the position. From the center of the calcite.
Can you predict from the electrical field, this kind of self-potential, can you predict how many particles will be needed to satisfy it, like in the diffuse double layer type of consideration?
So actually in this diffusophoretic mobility, you have all these kind of parameters that are taken into account. So what is taken into account is the difference in diffusivity of the ions that will lead to the electric field, and you have also the properties of the particles and especially of the electrical double layer. So depending on the particles, everything is in this parameter. Yeah.
My question is about not the dynamics, but the ultimate stationary state that satisfies the electrical field. How many particles are needed?
How many particles are needed?
To satisfy that self-induced electrical field. Can you predict it in advance? Like in diffuse double layer, I can calculate from the amount of defects in the clay how many cations I need.
For the salts, so what I know is that it works better for lower concentration, but at higher concentration you have some, so it does not really work anymore, but yeah, I guess, yeah, probably, I don't know. Yeah, in terms of the salts, yeah. Yeah, because there have people that have looked at also mixtures of different salts, because here it's just for two different species, but you can also look at mixtures, so yeah, probably you can do that. So then the idea with this kind of results is to see if we can go towards remediation that will be aided by diffusophoresis, meaning that, for example, if you, in the context of CO2 sequestration, where you want to avoid your CO2 to go back to the aquifer or to the atmosphere through fractures that are dissolving, you could actually target target mineral reaction with colloids that will like fill your fracture or that will precipitate and close the fractures, and it can also be used to target a contaminant in the same way. So without I have the same kind of take-home message than Jenna, that yeah, I think that combining microfluidic experiments with modeling, but also with high resolution post-processing techniques really help us to have a better understanding of the mechanisms that are happening, to provide data also in some cases. I have not shown example here, but to provide data to validate the models and then use the models to also improve large-scale models. And finally, I want to advertise for one last poster. It's the one of Walid, who is working on another part of colloid transport. He is looking at pore clogging using colloids in using microfluidic devices, and he also has a poster if you are interested in that. So with that, thank you.
Thank you, Sophie, for the presentation. You can open up for more questions.
Yes. I missed whether the calcium
Calcite.
CO3.
Sorry?
Calcite.
Calcite, yeah.
I missed whether it was producing net attractive or repulsive conditions. I saw all the colloids were negatively charged.
So in our case, so it's supposed to be attracting negatively charged particles, and it's supposed to, and for positively charged particles, they are pushed away. But in our case, the positively charged particles that we use, their zeta potential really lead to very, very slow diffusophoretic velocity, so we cannot actually see this effect with the ones that we tried. They were more like a control experiments. But with some other kind of positively charged particles, you can have also an effect of exclusion.
Did you still get the same buildup around?
So then if you have the exclusion, I guess you will not have the... So for example, if in our case, if we have the positively charged particles, no, they would just, when we have reaction, they will just flow around the calcite. So they will not attach. They will just, they will just, it's the same case and with no reaction. They will not build up. Yeah. Yeah.
Thanks for the nice talk. Can you elaborate a little more how this could be used for remediation? For example, dissolution of contaminants lead to the charge imbalance?
So for example, so for example, if you have a contaminant that is trapped, oops, I will go this way. Okay, I'm trying. Okay, this is this. So for example, if you have a contaminant that is trapped and that slowly dissolves in water, and that is releasing some species in water, locally you will have a concentration gradient of this species. And then if you choose, then you have to choose your colloids that will match the concentration gradient that you want to target, so you are sure that they will be attracted with it. And then the idea is to say that we will be able to deviate this colloid from the main flow. Here it's the main streamline of the flow, but we'll be able to deviate that to bring it to the contaminants. And then either the colloids will attach to the interface and display and help to displace the contaminant, or in some cases it can react with it.
On the slide that you showed the experimental setup, I saw that you have, for the solutions, you have different pH. Is there any reason that you have different pH values for?
Yeah, so the main reason is that for the positively charged particles, for some kind of particles, we were not able to use super low pH, or the particles were aggregating. So, but at the end, it's true that I put that there, but at the end what I presented today was mostly the low pH and the one with no reaction. So I could actually remove this information.
The particles themselves be contaminants.
So so it's true that in this case we want to use particles for to drive them, but we also think that diaphoresis effect might be important in some cases in porous media to drive particles, and your particles can be bacteria, your particles can be clay. So maybe it's also an important way of moving contaminants also, especially to dead-end pores, where usually they will not go with the main flow, but with diaphoresis they can attain dead-end pores.
So in your capillary experiments with the different velocities, it appeared that things behaved more or less as we expect. But there are a lot of open questions actually in how these things happen, particularly in the fingered flow business. And what we suspect is happening is time-dependent wettability. That actually surfaces as they get exposed to liquids and different, either dried or wet, that the surface chemistry takes time to take on its properties. Have you seen, what about exploring some of these questions that are not very well understood? And what are you thinking about in terms of understanding better some of these wetting processes and that are beyond just simple geometry?
No, it's true that it's a very important parameter, and especially so when we use PDMS, it's not very, so the wettability of PDMS is not stable, especially if you, so it's hydrophobic, and but if you expose it to water, it will become hydrophilic. So here in our case, because we wanted, we did not want to, in this case, to study the effect of wettability, so we treated our microchannels so to have a uniform wettability and to be sure that it will stay, it will not change with time. But yeah, it will be interesting to look at different wettability. So now we have also, actually we have one project where we have channels with different kind of wettability depending on where you are in the channel, and we can look at how an interface is invading this kind of channel. So yeah, this is the kind of thing that we can look at with this kind of experiments. It will be interesting. Yeah.
Thank you. I was having a follow-up question on can you have the particles to be eliminated as well? And then you answered that it could be bacteria that should get out of, or would it then be a charge-driven process as well, or? Yeah, so with bacteria you can also have chemotaxis, which is another process, but due to the charges, yes. Okay.
Well, thank you again, Sophie.